So the first data structure that we're going to cover is arrays. But before we even get into that, let's first understand what even is a data structure. Well, as the name implies, it's a way of structuring data. But in our case, we're talking about computers. So we're going to be structuring this data inside of RAM. Let me show you what I mean. So suppose that this is our RAM in this case, and RAM is basically where all of our variables are going to be stored. So as we write code and as we use array data structures, let's say that this over here is our array. Even though maybe we don't quite know what it is yet, we know that this is going to be stored in RAM. Let's say we have a 1, a 3, and a 5 in our array. So this is the information that we're trying to store. Now, how are we going to store it in RAM? Well, first of all, RAM is measured in bytes. It's common for many computers to have, let's say, 8 gigabytes of RAM. What do we mean by gigabyte? Well, giga in this case means about 10 to the power of 9. So let's say that's about a billion. But the more important question is, what exactly is a byte? Well, a byte is nothing more than 8 bits. So the next question is, what exactly is a bit? A bit can be thought of as a position that can store a digit, but the restriction on the digit is that it can either be a 0 or a 1. You might already be familiar with this. Zeros and ones are the language of computers. And as you can already see, individual bits can form multiple bits, which can form bytes, which can form RAM, and RAM can be used to store advanced data structures. But now let's get back to what arrays are. Now in this case, we have an array of integers, as you can tell. Now don't worry, I know I still haven't told you what an array actually is. So in this case, we have an integer 1. How can we store this integer 1 in our RAM? Well, we have to store it in terms of bytes. Now it's pretty common for integers to be represented not by a single byte, but actually as 4 bytes. So what that would mean is instead of using 8 bits, we would actually have, let's say, 32 bits. I'm not going to draw all of them out, but you can assume that we have in total over here, we have 32 bits. So how are we going to represent this 1? Well, we're going to talk about this a little more in depth later in the course, but for now, I'll just tell you that it's going to be 31 zeros, and then all the way at the end, we're going to have a single 1. So what's important here is that we have a way to take this 1, represent it in terms of bytes, and then we're allowed to put that into RAM. Now, while RAM can be thought of as a contiguous block of data, it also has two components to it. Of course, we're going to be storing values in our RAM, but every value is going to be stored at a distinct location, which we call an address. Now, I've put a $ in front of every address just to kind of distinguish that between the values that we're going to be storing. But what you can see here is that the first address is 0. Now, as we store an array in RAM, we don't always get to choose what location it's going to be at. But one thing about arrays is that they're always going to be contiguous. What that means is here we're going to be storing the 1. Here we're going to be storing the 3, and here we're going to be storing the 5. So nothing is going to be in between the 3 that we have stored over here and the 5 that we have stored over here. Nothing is going to be in between that. But if that's the case, why am I incrementing the address by 4 every time? Shouldn't this be stored at 0? This should be stored at address 1. This should be stored at address 2. Well, remember, each value takes 4 bytes to store. So this doesn't represent 1 byte, it represents 4 bytes. So we're storing 32-bit integers. That means they take 4 bytes to store. Now this might seem very straightforward, and it is for the most part, and that's because arrays are considered the most simple data structure. We just store them pretty much the same way that we're representing them here. In memory, they look the exact same as they do the way we use them. A contiguous set of values. Now in this case, we're storing integers, but we could be storing other values as well. Let me show you what it would look like if instead we were storing characters like ABC. Characters are stored pretty much exactly the same, contiguously as we would expect. But you notice the address is a bit different. In this case, we're incrementing by 1 as we add a new character. That's because each character actually only takes 1 byte to store in memory, not 4 bytes. At least that's the typical case if we're storing ASCII characters, which isn't super important to know. What I'm getting at though is we can